Good day everyone. Have you ever seen a tree? So a tree look like this. A tree has its own parts, the leaves at the top, the branch, and the root at the bottom. But in computer science, it has its own tree, but in reverse type. So, a tree in computer science has its own root at the top, branch, and leaves at the bottom. So, introduction to tree. A tree is a finite non-empty set of elements. It is an abstract model of hierarchical structure and it consists of nodes with a parent-child relation. So, a tree is a widely used data structure that organizes data hierarchically. Hierarchically means organization or arrangement of elements in a hierarchical or nested structure. A hierarchy is a system of structure in which elements are ranked or ordered according to their level of importance, creating a series of levels or layers. It is a collection of nodes connected by edges, where parent-child relationship with other nodes. The topmost node in a tree is called the root, and the node with no children are referred to as the leaves. And now, we have it's called the tree terminology. So, first, we have the root. So, a root is a node without a parent. An example of that is the A. And then, we have it's called siblings. Node shares the same parent. So, example of that is E and F because they share the same parent, which is node B. And then, there is what we call internal node. A node with at least one child. An example of that is the A, B, C, and F. And then, the external node, or we could say the leaf, a node without children. Example of that is the E, I, J, K, G, H, and D. And then, the ancestors of a node. So, parent, grandparent, grandparent, and so on. So, an example of the ancestors. So, we could say node F. The ancestors of node F is B and A. Another example is the node G. The ancestors of node G is C and A. And then the descendants of a node. Descendants of node is the child, grandchild, grandchild, and so on. So example of that is B. The ancestors of B is F, I, J, and K. Those are the examples of ancestors and descendants. So depth of a node, the deep number of ancestors, and then the height of a tree. Maximum depth of any node. So maximum depth of the example is 3. And then there is what we call the degree. Degree of a node, the number of its children, the degree of a tree, the maximum number of its node, and then there is what we call the subtree. Tree consisting of a node and its descendants. So there are 5 types of tree. First is the general tree, second is the binary tree, third binary search tree, fourth AVL tree, and the last is play tree. And then the first type of tree is the general tree. If no constraint rule is placed on the tree's hierarchy, a tree is called a general tree. Every node may have infinite numbers of children and general tree. The tree is the superset of all other trees. So here's an example of general tree. So as we can see, there are 4 child nodes, there are 1 child node and 2 child nodes. So in the first top, there are 4 child nodes, but in the second column, there are only 1 child node, and in the middle, there are 2 child nodes. So in this case, general tree has no limitation on how many child nodes it have. So it can be 3 child node, 4 child node, or 1 child node, or 0 child node. So there is no limitations or restrictions about this kind of tree. So the second type of tree is the binary tree. The binary tree is the kind of tree in which most 2 children can be found for each parent. The kids are known as the left kid and the right kid. So here is an example of a binary tree. So as we can see in the picture, there are only 2 in one child node in every parent, because the binary tree consists only 2 in one child node, not exceeding into 3. Because we can identify a binary tree using the left and the right. binary tree traversal. A tree traversal is a specific order in which to trace the nodes of a tree. So there are three common tree traversals. The in order, left, root, right. The pre-order or the root, left, right. In the post order, the left, right, root. So in binary tree traversal, so here's an example of binary tree traversal. So in order, so first we must identify the leaf of the binary tree. So the leaf are the 3, 7, 13, 18, and 23. So first we will go to 15 and we will not print the 15. 5, we will not print the 5, and then we will go to 3. So we will print the 3 because it is the left side, and then we will go back to 5. We visited second time 5, so we will print the 5, and then we will go back to its right. We will not print the 12, and then we will go to the left. We will not print the 10, and then we will go to the left again. See 6, so we will print the 6, and then it has no left, then we will go to its right. So 7, we will print the 7, and then we will go back to the top, and then the 10 is visited second time, so we will print the 10, and then we will go to 12. So 12 is visited second time, we will print the 12, and then we will go to its right. So we will print the 13, and then we will go back to 12. 12 is printed, and then we will go to 5, printed, and then we will go back to 15, and then we will go back to 6. We will go to 16. So we will print the 16, and then we will go to 20. So 20 has left and right, so we will go to its right. So we will print the 18, and then we will go back to 20. 20 is visited second time, so we will print the 20, and then we will print its right, or the 23. So that's the last in order. So it is 3, 5, 6, 7, 10, 12, 13, 15, 16, 18, 20, and 23. So the second type of binary tree traversal is the pre-order traversal, or the root, left, right. So in the example, we will first print its root. So we will print the 15, and then we will go to the left, which is 5. We will print the 5, and then we will print the 3, and then we will go back to 5, and 5 is printed. We will go to the right. We will go to 12, and then we will print the 12. We will go to left, which is 10. We will print the 10, and we will go to 6. We will print the 6, and then we will go to its right, which is 7. We will print the 7, and then we will go back to 6, to 10, to 12, and then we will print the 13, and then we will go back to 12, 5, 15, and then we will arrive at 16. So we will print the 16, and then we will go to its right. We will print the 20, and then we will first go to its left. So we will print the 18, and then we will go back to 20, and then we will go to its right, which is 23, and we will print the 23. So the pre-order is 15, 5, 3, 12, 10, 6, 7, 13, 16, 20, 18, and 23. So that's the pre-order in binary tree traversal. So in binary tree traversal, last is the post order. So it is a tricky one. So first we will go to 15. We will not print the 15, and we will go to 5. We will not print the 5, and then we will arrive at 3. So we will print 3 because it is a left, and then we will go back to 5. We will not print the 5. We will go to its right in the 12, so we will not print the 12. We will go to its left, 10. We will not print the 10, and then we will go back to 6. We will not print the 6, and then we will go to its right. So we will print the 7 because it has no left and it has no right. So we will print the 7. We will go back to 6. When we visited the node second time, we will print it. So 6 is visited second time, so we will print the 6. And then the 10 is visited second time, so we will print the 10. Then we will go back to 12. So we can see that it has a right, so we will go to its right. We will print the 13, and then we will go back to 12. We will print the 12, and then we will go back to 5. The 5 is visited second time, and we will print the 5, and then we will go to 15. We will not print the 15. We will go to 16. we will not print the 16, we will go to 20, we will not print the 20, and then we will go to its left, so we will print the 18, and then now we will go back to 20, we will not print the 20, we will go to 23, we will print the 23, and then we will go back to 20. 20 is visited second time, so we will print the 20, and then we will go back to 16. 16 is visited second time, so we will print 16, and then we will go back to 15, which is the root, and then root is visited second time, so we will print the 15. So the post order is the 3, 7, 6, 10, 13, 12, 5, 18, 23, 20, 16, and 15. Binary search tree. Binary search tree, or BST, is a binary tree extension with several optional restrictions. The left child value of a node should in BST be less than or equal to the parent value, and the right child value should always be greater than or equal to the parent's value. So a tree is a collection of nodes with edges that connects them. The nodes are organized in two levels, and the top level is called the root node. Each node can have child nodes. In this case, number 3 is a parent node, and it has a left child and a right child. And the left and the right child are called siblings because they share the same parent. The 1, 4, 6, and 9 nodes here are called leaf nodes because they don't have any child nodes. In a binary tree, each node can have up to 2 child nodes, a left child and a right child node. Number 5, right subtree includes everything. This triangle, which is a tree in itself. Under node 5 is left subtree, includes node 3, 1, and 4. Node 4 has ancestors, which are simply every node between itself and the root node, and node 5 has descendants, but basically every node below it all also children node and their children's nodes, and so on in a binary search tree, and node is greater than every node in its left subtree. So, for example, 1, 5 is greater than every node in left subtree. 8 is greater than every node in its left subtree. Node 5 is greater than the 2 in its left subtree. Number 24 is greater than 19 in its left subtree, and so on. And each node is less than every node in its right subtree. So, here we can see that node 15 is less than all the members of its right subtree. 24 is less than the members of its right subtree, and 8 is less than the members of its right subtree, and so on. These two characteristics makes a binary search tree. 3 operations where have insert, find, delete, and so for a binary search tree insertion, we start at the root, which is node 15. Let's say we want to in at 12. We're always going to insert a node as a leaf. So our first comparison will compare 12 to 15. It's less than 15. We'll take left child. We compare 12 to 8. 12 is greater than 8, so we take the right child to compare 12 to 11. 12 is greater than 11, so we take the right child. We'll compare 12 to 13. 12 is less than 13. 13 has no children, so we add 12 as a new left child for node 13, so we can see that number 12 is inserted as a leaf node. For a binary search, we find operation, we also start at the root. Let's say we want to find out 19. Our first comparison is 19 less than 15. It is not, so we take the right subtree. Is 19 less than 24? Yes, it is, and there we find 19 already, so find operation is pretty simple. So binary search tree delete. So binary search tree delete operation, there are 3 possible cases. Either the node you want to delete is a leaf node, it has 1 child, or it has 2 children, and we'll look at each case separately. So first, let's say we want to delete a node with node is a leaf node. Now in this tree, we can see that the node 2, 6, 12, 19, and 25 are leaf nodes. So if we want to delete one, we can simply delete it without affecting the rest of the tree. Now we want to delete a node that has 1 child. And in our tree example, here we can see that node 11, 13, 28 all have 1 child. If we want to delete, for example, node 11, we can see that 11 is node 8 right child. So we make 11's only child 13. its right child. In other words, 13 takes the 11th place and then we can delete node 11. Now, note here that node 12 stays attached as 13's left child and that does not change. It does move up a level in the tree, but it stays attached 13 left child, so 13 sub-tree is not affected. Now, if we want to delete the operation with two children, let's say we want to delete node 24, which we can see that has a left child and the right child, we find the next higher node. So we do that. We look at node 24, we follow the right sub-tree node 28, and then we look at left child, and left child continue down to the leftmost path until we get to the bottom. In this case, there's only one edge, number 25. So that is the next highest node from 24. So in this case, we can change the 24 to 25. And the delete number 25 in the last case, let's say we want to delete the node that has two children. This case, node 4. So 4 has left child and the right child. So first, we're going to find the next higher node, which is 6. We change a 4 to a 6, and then we can delete node 6. And since the delete operation is done recursively, the 7 basically takes 6 is a place and the 6 is gone. So the advantage of binary search trees, speed, we can insert, delete, and find in big 0 of edge speed, which is big 0 of the height of the trees. That means that an unbalanced binary search tree with the 10 million nodes, find, insert, delete operations takes only on the order of 30 comparisons, which is incredibly fast. That wraps up our introduction to binary search trees.